Hello, students. I'm going to hit us up with some 4.3. This is the last section before test 2. This one does involve things about divisors, but also complements that with multiples. Remember how those words work together. So we've got the idea that two numbers could have both multiples that might be in common, as well as divisors that might be in common. And we're going to kind of check that out as we roll through. Let's see here. So greatest common divisor. There's a little description here about kind of what it is, but I mean, don't read too much into it. And honestly, depending on where you grew up in this country, you might have heard this not as greatest common divisor. You might have heard it as greatest common factor. So there's two ways to say it. Both of them mean the same thing. Remember, 2 is a divisor of 12, which means 2 times 6 equals 12. By definition, that makes 2 a factor of 12. So there are a couple ways you can go about doing these. Let me get my annotation tools ready to go. But again, just you need to think of it as more than one number. So if you're thinking about more than one number, the example they used up here was with 24 and 36. So with 24, I can think of all the things that divide 24. Now, if you need to, if you struggle with this, use prime factorization. 24 turns out to be 8 times 3. That's 2 cubed times 3 to the first. Then the factors are all of the factors, and you can just go in order. All of the things that divide 2 cubed. Now remember, how do we find how many of these things there are? We know there's 4 because it goes in order of the exponents, 2 to the 0, 2 to the 1, 2 squared, and 2 cubed. So there's 4 total factors here. From the 3, we add 1, and we get 2 factors from that. Then we multiply those together to get the total. So for the number 24, there will be 8 divisors total. Now, if you want to find those divisors quickly, yes, you can just, for small numbers like this, maybe you're golden, just kind of thinking of all of them. But if not, here's a quick way to write them all out. Think of the powers of 2. That's what I have right here. The way I do it is I simply write all the powers of 2 down in order. I'd say 1, 2, 4, 8. Perfect. Now I bring in the powers of 3, because really what I have in this first column is I've multiplied by 3 to the 0, which is 1. So in the next column, I just multiply everything by 3. 3, 6, 12, 24. And that's how I get my list. Okay, so that's 8 of them done. I have all of them. But again, could you have gone and just kind of found all the factors kind of thinking about it? Yes, you could. And if you're really good with the speed of that, sometimes you can get there just as quickly. What you'll notice here is I did 1 times 24. Once I find 2, I think 2 times what? So I find my factor pairs. So if you find factor pairs, that's great. If you just find the factors, that's also fine because you have exactly the same list. Let's do the same for 30. 30 is 2 times 3 times 5. Okay. So again, could I go through and find factor pairs? Yes, of course. So I could do 1 times 30, 2 times 15, 3 times 10. 4 doesn't work because there's an exponent of 1. 5 is good, so 5 times 6. And I can notice here, 5 times 6, I can't go up to the number 6 because I already have it included. So this would be all of them. So it looks like there are 8 factors as well. Now I could check that with our little tip. Here's a 1. 1 plus 1 is 2. 1 plus 1 is 2, and 1 plus 1 is 2. So 2 times 2 times 2 gives me 8, and that works perfect. Okay. So if I was trying to find all of these using the other technique, I simply list all the things that divide 2. That's a 1 and a 2. Then I'd find all the things that divide 3. So I multiply by 3. So I have the 3 and the 6, right? And then I have the things that divide 5, which would be things that divide 5 would be a 1 and a 5. So I can go back to the beginning, multiply by the 5, and I'd have 5 and 10. And then I have the 2 times 3 times 5. So I have all the factors together as I do it, right? And then I also have the 3 times 5 that hasn't been included yet. So I have to think about those additional pieces that come in. I have 15 and 30. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 and 8 for these, your choice. But now what I want you to notice is this. If you were to consider all of the divisors, right? I'm going to do a Venn diagram for this. I think it's probably the easiest way to think about how they connect. So what I want you to do is I want you to think over here. Here's all the divisors of 24. Okay. And then next to it, I'm going to put all the divisors of 30. So now what I want you to do is I think, where would I put each divisor? And of course, there are other numbers outside here. There's a lot of them, but I'm really only going to focus on what's inside. So the number 1 is in both of them. So I'm going to put that in the intersection. The number 2, so I'll cross that off because I got that done. The number 2 is in both of them, so that goes in the intersection. The number 3 is in both, that goes in the intersection. The number 4, 4 is only in the 24, so make sure I put that in this one, but not in D30. The number 5 is in the second, but not in the other, so I'll put a 5 over here. The number 6 is in both, so I'll put a 6 in the middle. And you knew there'd be a 6 in the middle because 2 and 3 both go in. Now remember from 4.2, if 2 and 3 both go in, you get 6 for free. Next up, let's see here. I have a 10, a 15, and a 30. None of those show up here, so I'd put them down here. 10, 15, and 30. And also over here, I have 8, 12, and 24. Okay. All right. So now what, right? Now I want you to think about this. This chunk, oops, I didn't mean to do blue. Thought I was on yellow. This chunk that's in the middle is all of the things that we would call common, right? The things where they intersect. These are the set of common divisors. And so the set of common divisors, you would have to say, oh, well, I have a 1, a 2, a 3, and a 6. Now here comes a fun fact. Every single pair of numbers that you can think of will have a 1 as a factor, right? 1 divides every number perfectly. So everything's going to have a 1. So that would be like, if you were really thinking about the least common divisor is going to be 1. And it's always going to be 1, right? It's always going to be 1. So yeah, it's really not a interesting math problem to kind of say, what is the least common divisor? Because the answer would always be 1. But going up, sometimes you may only have a 1. In this case, we get a 2, a 3, and a 6. So we actually do end up with a greatest common divisor of 24 and 30, and it turns out to be 6. Okay. So anyway, that's the idea of common divisors. So again, least common divisor, I'm just going to put kind of a wrinkly face like, why would you want to know that? It's always going to be the number 1. But greatest common divisor, okay, now that might help me solve some problems. If I need from both of these, like from a group of 24 and a group of 30, what's the biggest group sizes I can make that would be common? Boom. Now I know I can make groups of 6, and everybody will have the same size groups in that class. Not going to be an issue. Okay, now notice over here in the D30 class, they could make a group of 15, but the other side could not make a group of 15, so that would not be a common factor or a common divisor. So that's pretty cool. That is pretty cool. And again, the prime factorization is helpful there. I think they show it on the next page. So I'm going to say there is a quick way to do it with the prime factorization. I believe they show it here on the next page. So we'll go over to that. Okay, so what's the techniques you have for finding the greatest common divisors? Step 1, create an intersection of sets. List all of the divisors in order and find where they overlap. The intersection of those is known as the set of common divisors, and then you can find the greatest in that set. Okay. The other way is, like I showed you here with Venn diagrams. You can see what's in both of them, what's in one, and what's in the other. Okay. The next one, though, is the prime factorization technique. Let me show you this one with the with the 24 and the 30. Yeah, because I think if you see it with 24 and 30, then when we do a bigger example, I think it'll make a little bit more sense. Okay, so here we go. All right, let's chat. Here we go. Give me 24 and 30 on the clock. So what we said earlier is 24 is equal to 2 cubed times 3 to the first. Now 30 was equal to 2 times 3 times 5. If we were to write those out, each would have an exponent of 1. So now instead of looking at the number, we're going to kind of ignore that number temporarily and just look at the prime factorization. So now remember what we talked about in class. I can tell if I call this A and this B, I can tell that 2 does divide A and 2 does divide B. And the reason is 2 to the first is less than or equal to a number in each of them. So 2 divides A and 2 divides B. Okay, so now let's move up. Let's move up to 2 squared. Does 2 squared divide A? And what we're looking at, what we're comparing is we compare that to the exponent here. And so yes, this one works just fine. 2 squared does divide A because my exponent is not greater than the exponent that exists in my number itself, prime factorization. But over here on this side, 2, when I check, the exponent is a 1. Uh-oh, we've got a problem. 2 squared does not divide B. All right? So that means the biggest prime that divides both of those so far is the number 2, and we would just use 2 to the first power. Okay, so now in a sense, we're done with 2's. And the reason is, even if I went up to 2 to the third power, we already know it won't divide because 2 to the second power didn't divide. The number 4 didn't divide. If 4 doesn't work, I guarantee you 8 is not going to work. And likewise over here, if I did raise this one up to 2 to the third power, it's great. Yes, it still divides, but who cares? We're trying to find things that are common, so we're actually kind of done with the 2's at this point. Okay. Let's move on. We'll move into the 3's. So does 3 to the first divide A? Let's check. Exponent of 1, exponent of 1. Yes, it does. Does 3 to the first divide B? Check. Yes, it does. Now, it really wouldn't make a lot of sense to continue going with the 3's, although you could ask yourself, does 3 squared go in? And it would fail in both cases because you can see each one of those is just an exponent of 1. So I would put a 3 to the 1 over here because those are common. Okay. And the last piece that we would have to think about is a 5. So let's see here. 5 to the first does divide B. And I check the exponent here. And I've heard students say, but there is no 5 on the left-hand side. But I want you to think, it's really 5 to the 0 then. There is a 5 there. It just happens to have an exponent of 0, which represents basically the number 1. And so if you say, does 5 to the first divide A, you go up here and you would say, well, 1. And 1 is bigger than 0. So I'm sorry, it does not. So it does not divide A. So that means 5, any form of 5, any exponent on 5 is not common. So there we go. And this right here would be the greatest common divisor of 24 and 30. It's just that product, 2 times 3, which turns out to be 6. Right? So now if we were going to try this again with other numbers, which I'm going to do right now, then as you look for it, okay, you know what? Let me rewrite this. That part got a little messy. And I'll rewrite what our final result was. Okay, so we said 24 is 2 cubed times 3 to the first. 30 is 2 to the first, 3 to the first, 5 to the first. Okay, and then the GCD of 24 and 30 turns out to be 2 to the first, 3 to the first, which is just 6. Okay, so now let's go with bigger numbers then, shall we? Let's go with bigger numbers. We can choose numbers and then prime factor. For this next example, I'm just going to give you the prime factorization to save us a little bit of time. So now let's say I had 2 to the fifth, 3 squared, 5 to the fourth, and 7 to the first. That's my first number. And my second number is 2 to the 4th times 3 to the 1st times 5 to the 5th times 7 squared. Big numbers. This would take a while to find the prime factorization if we had them all multiplied out. They'd be pretty big numbers. But now let's take a look. What is common to both? And we're looking for the biggest thing, the greatest thing that's in common. Okay. So the GCD of A and B is what we're looking for. Let's start with the prime factor of 2. Okay. So what is the greatest amount of 2's that'll go into both numbers? Let's see here. Now in B, I know 4 2's are in one of those numbers. That's great. I have 4 of them. And the other one I have 5. But again, it has to be the greatest number that's in common. So I would actually put down 2 to the 4th, because that's the most that could go into B. I can't get any more 2's out of that. Next up, we'll move on to the 3's. What's the greatest amount of 3's in both numbers? And the greatest in both numbers is just 1. Yeah. Let's see here. Next up would be the 5's. Probably should have chosen a different color. Let's see here. Here's the 5's. Now, what's the most 5's that are in both numbers? And we'd have to say, oh, that's 5 to the 4th power. Okay. And lastly, what about these 7's? What's the most 7's that's in both numbers? And the answer is 7 to the 1st power. Okay. So there is our GCD. Yeah, if you want to multiply it out, you can. Notice a 2 times 5 makes a 10. And I have 4 of those. And 3 times 7 is 21. So I really have 21 times 10 to the 4th. And 10 to the 4th is 4 zeros when I multiply. So, oops, I don't know why I wrote 12. 2, 1, and then 4 zeros. And that is it. There's my GCD, 210,000. Love it. That's it. That's how you can find GCDs. Hopefully, you're starting to pick up on this beautiful trend. Prime factorizations are not just cool, they are amazingly efficient. If I want to find, look at this answer. It's 2 to the 4th, right? Well, there's a 2 to the 4th here. There's a 3 to the 1st. There's a 3 to the 1st here. 5 to the 4th. There's a 5 to the 4th and a 7 to the 1st, 7 to the 1st. So I hope what you're seeing is I can get that GCD equals, basically put the exponent that is the smallest. That is the smallest. So if both of them have 2's, you have a 2 to the 5 and a 2 to the 4, you'll use 2 to the 4 because it will divide each of them. If you have a 3 to the 1st and a 3 to the 2nd, you'll use 3 to the 1st because it divides both of them. Now over here, what if we had one other number? What if one of the numbers had an 11 in there, like 11 to the 1st? You'd say, but the other one doesn't have a common piece. Just remember, you could always use 11 to the 0. And then we have to use the one that's the smallest. So even though there's an 11 in one number, there's not another 11 in the other. So we really would kind of ignore it or put a times 1 at the end. And that is how you can find the GCD pretty quickly if you have the time to go through and find the prime factorization. Pretty nice technique, pretty nice way to do it. Okay. Now, big fact here, new terminology. If two numbers do not have anything in common factor-wise, we call them relatively prime. Okay, so relatively prime, all it's saying is the GCD is 1. Okay. Let's see here. Common issues with students in this section, probably a problem like this. GCD of 0 and 13. So GCD of 0 and 13, the most common thing is to say it's 0, but remember, it has to divide each number. 0 does not divide 0. Okay, so 13, I know 13 divides 13, and I know 13 divides 0. And I can't get any bigger than that because nothing bigger than that will divide the 13. So the GCD would just be 13. Okay. Let's see here. Other ways to go about doing it. Let me see if I can kind of show you what I think is kind of a quick way as well. So yes, you can always do prime factorizations. The only issue is, I'm not going to lie, prime factorizations are super cool and they're very helpful. The only issue is it takes a little while to find those sometimes. So let's take a look at the number 108 and 72. So when I look at this, I look and I say 72. I know 72 is 9 times 8. Well, gloriosi, there you go. You nailed that piece. Okay. Now let's go to the top number because it's a 108. And if I do my divisibility test and I add the digits together, that gives me 9. And 9 means it's divisible by 3 and 9. So I know there must be a 9 in this number as well. So if I was thinking about that, I could say, well, 108 is like 90 plus 18, which is 10 and 12. Aha. So what I've really done is I've broken off a 9 for each of these, which to me is pretty quick. I'm just going to go down here and I'm going to write 9 times 4 times 3, because that's what 12 is. And down here, 8 is 4 times 2. And so what I can see here is I can see factors that match up perfectly. Now, this one doesn't match up perfectly. So I would be able to say that the GCD of 108 and 72 is 9 times 4. I didn't have to break it all the way down into primes. I look for things that are in common as divisors, and then I can just list those as well. Okay, so if you understand the idea of the problem, you may not have to go quite as far. Okay. Now, if you spotted it right off the bat, 108 turns out to be 36 times 3, and 72 turns out to be 36 times 2. And so if you got here, you'd say, well, these aren't common. There's nothing in common between them. So my GCD is just 36. Okay. Pretty convenient and pretty quick there. A couple different techniques. I hope at least one of these sticks with you. There's a calculator method, and then there's what's known as the Euclidean algorithm. And so I think the Euclidean algorithm, this is actually pretty cool technique here to do this one. But it's pretty dense in terms of the text. So I notice most of the time students kind of like to see it as they're doing it. And so we're going to go ahead and do that one. They even put in a flow chart here. But they do describe the idea here in theorem 4-18. But let me link back. Let me go ahead and share just a whiteboard screen. Let me link back to what we did already in class. So let me just describe kind of where I'm headed. We've already talked about if A divides N and A divides M, then A divides N plus M. Right? So again, if it divides one number and the other, it divides the sum of the two. We also have another theorem that said it also divides if you subtract them, because once you can make groups of 7 out of something, let's say, right, then it doesn't matter if you add or subtract because they were all groups of 7. So you're just taking away some groups of 7 and you're left with more groups of 7. So it could be plus or minus, could be addition or subtraction. Okay. So now let's see what that says. So if I have a number here, n, and I'm telling you that 7 divides n. You know that. And 7 divides m. Well, then we know that 7 must divide n minus m, which is going to be smaller than n. Okay. So here's the idea, though. That works great if it's a 7. What if, and this is the big what if I don't have a 7 here? What if I don't know what number divides both of them? So what if I'm looking for this common divisor? Then maybe I should just call it D. So if D divides N and D divides M, then D has to divide the difference between those two. Okay. And remember, if D does divide M, then D must divide any multiple of M. So like some multiple of M. So that's, again, these are two different theorems. One is theorem 4-1, and the other is theorem 4-2, A and C. Okay. So that's interesting because what we're going to do now is we're going to kind of show how this could work. And I'm going to show it with the two numbers that we just did, which is 108 and the number 72. So what I want you to do is I want you to think there is some number, and maybe it's only the number 1, but there is some number that divides both of these two. And remember, if it does divide both of them, then it must divide 108 minus 72. 108 minus 72 turns out to be the number 36. Aha! So I know that D divides these two numbers. You know what? 36 is smaller, and I know D has to divide 36 as well. So now in order to continue this, maybe I will pick, you can pick any of these to continue on with, but I'm going to pick the two that are kind of the smallest. Okay. So now I'm going to repeat the process. I know D divides 72 and I know D divides 36. So that means D has to divide 72 minus 36. Okay. Well, 72 minus 36 turns out to be 36. And since it divided one group of 36, D has to divide 72 minus two groups of 36, which turns out to be 0. So you need to find a number D that divides 36 and also divides 0. And as a big hint here for the 0, as long as D is not 0, this is guaranteed to be true. 42 divides 0, 67 divides 0. So this bottom one really doesn't do us much good, although it does indicate for us a stopping point. Once you get down to 0, you don't have to go any further. And your last number has to be the greatest possible divisor in common. So we already saw that the GCD would be 36. Here we can see it is 36, and we can get there fairly quickly. Okay. So that is the first little piece we have with the Euclidean algorithm. Now we're going to pick a couple other numbers, and let's see here. I think in the book they used, let's see here, 676 and 221. Okay, so 676 and 221. So what we're going to do is we're going to kind of create a process. This process to get to a result is known as an algorithm. And this algorithm was first kind of created and used by someone called Euclid. And that's why we will call this the Euclidean algorithm. So the Euclidean algorithm. All right, let's take a look at it. What it says is this. You know that 676 has some divisors, and so does 221. If you want to find something that divides both, you could actually go through and subtract 221. Now notice that'll get you something in the 400 range. But whatever your number is that divides both of these, it has to divide another group of 221 then, which would be 440 something. That's great. But if it divides that many, which what does this turn out to be? 442. And when I subtract, it gives me 234. Oh, I could actually put another group of 221 in. So what Euclid did is he said, instead of thinking of these as separate ideas, why don't we see how many groups of 221 can go into this number? And so you could actually go through and do the division. 676 divided by 221, just to find out how many times it does go in. And let's see, I'm grabbing my calculator here. And 676 divided by 221, it goes in 3.05, 3.058, da 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 da. Ah. So what I can come back and do is say the biggest I could probably use is 3 of these. Then take the difference and do 676 on your calculator. 676 minus 3 times 221. And the end result turns out to be 13. So here's what I now know. I know whatever number divides 676, and also divides 221 has to divide 13. So now what do I know? I knew that my magic number divided 676. The number I'm looking for has to also, oops, that's a little sideways. I don't want you to think of it as a fraction. It has to divide 221. And now, because of this piece, it has to divide 13. Phew. Well, we're not quite done yet. So let's take the smallest of these and repeat the process. Okay, so now whatever number I know has to divide 221. And it has to divide 13. My question is, I don't know how many groups of 13 are in 221, but let's see. Let's see here, 221 divided by 13 on my calculator. And my calculator says 17 right on the nose, no decimal point. So that means I get 0 out of this. And so I can come over here and say, so my magic number also has to divide 0, which again is kind of silly because every number divides 0 as long as you're not using 0 itself. So what we just found is that the GCD, the greatest common divisor of 676 and 221, is the number 13. So pretty convenient way of doing it if you don't want to go through and do prime factorizations. So let's kind of show the two side by side. I'll do another one that's in the textbook with 180 and 68. And again, I can't tell just by looking what the GCD is. I'm good, but I'm not that good, right? So I still use some of these techniques to help me to see what's in common. I could see there's a 2 in common, and the last 2 digits. It looks like there's a 4 in common there, so I know there's at least a 4. Maybe there's more. I'm not sure. But let's go from here. Okay, so if I was going to use the Euclidean algorithm, I would take my biggest number and I would subtract as many groups of the smaller number as I could. Now, in this case, how many groups of 168 are in 180? And turns out I don't need a calculator because there's only one. When I do the subtraction, 180 minus 168, the difference will be 12. Okay. Then the next one, I can come down and say, let me take the next biggest two, which would be 168 and 12, okay? And just say, how many groups of 12 are there in 168? Again, I'm going to need my calculator here. I don't have that one memorized. So 168 divided by 12 turns out to be 14. So once I put a 14 in here, it's 14 even. I get 0. You can stop, and your GCD is 12. And I should probably put it correct notation of 180 and 168. That turns out to be 12. Those two blurred together. There we go. GCD is 12. Now, that's one option to finding the GCD. This is the Euclidean algorithm. Okay. If you have really big numbers and it looks like it's going to be a real pain to factor, I would use the Euclidean algorithm. Okay, because it'll very quickly through division get you broken down. Within a couple steps, your numbers will be significantly smaller, much easier to work with. And sometimes you can just find the answer once you get there, once you see what numbers you end up with. Okay. All right. In the first couple here, it only took 2 steps. There will be some in the homework. Maybe it takes 3 steps or 4 steps if you're using the Euclidean algorithm. Okay. What are the other techniques I could use? Well, I could use my divisibility rules, right? I know 1 plus 8 plus 0, that gives me a 9. So 3 goes in and 9 goes in. Down here, 1 plus 6 is 7 plus 8 is 15. So 3 goes in. I know there's a 3 in there. So maybe I would just write out 180. There's also a 2 in here. I see a 2 definitely because it's even. So that's a 6. So I would write this as maybe 6 times 30. And I know this is even as well. So 168, oops. 168 would be 6 times something, right? And let's see here. 20 would be 120. So maybe I'll break this down and be like 120 plus 48. Okay, so that's 6 times 20 and another 8, so 28. Okay. So now I've already broken down, so I know there has to be at least a 6 in common. Each of these numbers is even, so I could write this down as 6 times 2 times 15, and this would be 6 times 2 times 14. Okay, and these have nothing in common, so my GCD would be 12. Right? So again, that's another way that is kind of a just straight factoring, not prime factoring. So this one does require more thinking. If you want to break it all the way down into primes, go ahead and divide it by 2. Okay, that's 2 times 90, but there's another 2. Okay, that's 2 times 2 times 45, and 45 is a 9 times 5. So my final answer here would be 2 squared, 3 squared times 5. 168. Why do I keep wanting to write 186? Sorry about that. So yeah, 168. So again, a 2 goes in there, definitely. 2 times 84. Put another group of 2 in there. 84 becomes 42. Put another group of 2. I get 21, and I get a 3 times 7. My final answer here would be 2 cubed times 3 times 7. And so if I was doing the prime factorization method from the 2's, I would extract a 2 squared. From the 3's, the biggest one I can use in both would have to be just 3 to the first, and the 5 and the 7 have nothing in common. So my GCD would equal 2 squared times 3, which is 4 times 3, or 12. 3 different techniques to find it. Totally up to you which one you prefer to use. Okay, let's jump back to our page over here. Okay, so this is demonstrating the Euclidean algorithm, and it says basically, hey, if you have 2 whole numbers, if it divides both of them, the greatest common divisor divides both those numbers, it also has to divide the remainder. And we showed why it has to divide the remainder, because the remainder is the difference between those pieces, and that's using the theorems we already know about. They do put in, like I said, a big picture here. I don't think you need this flow chart, but just remember, once I get down to a remainder of 0, that's what I end up with. So here's an example using the Euclidean algorithm, and these are pretty big numbers. Like I said, yes, I probably could factor them given enough time, but if I just start subtracting, I immediately get smaller numbers. And when if you were doing this problem, you could start with these 2 big numbers. You end up with a remainder of 1564, and you basically say, let me take the smallest 2 of these, and that creates my next step. So how many 1564s are in 2300, right? All right. So anyway, that's kind of the way that you can do it. All right. And yeah, you're kind of shooting, I should say, in this case, you actually can go over as long as you wanted to, because you could have reversed this. So if you end up like really close to a number, sometimes it's easier to just continue on with that. Let me see if I can find part of this example and show that. I think a lot of times students are like, oh, that's too bad. I was so close. Those numbers are pretty close. These numbers are pretty far away. Let's see here. Yeah, so here I used 4 groups of 2300. So I'm going to try this with 5 groups of 2300. Okay. So what I get with 5 groups of 2300 is I get 11,500. And if I subtract 10,764 from that, I get 736. Oops. Sorry about that. I get 736, which means if you had used this in your first step, you wouldn't have needed the 1564. You could have jumped straight down to the 736. And then you can pick 736 with your next smallest number, which would be 2300. So 2300 and 736. And so then you just say, well, how many 736s? 736 times 3 is like super close, right? 3 of those is 2208. So now I have 2208, which is 3 groups of 736, and I have 2300, and when I subtract, I get 92. So again, I'm getting down to the same place with 92 and 736. It's just taking me a little bit fewer steps. we need to, when I do the homework section, I'll probably grab one of those and kind of show a couple different ways to do it. I think it's good to see different ways. You might be like, oh, I totally understand one way. But if your way is really, really long, it may not be ideal. Okay. All right, let's see here. Then it goes to what do we do with the GCD of three numbers? And if you have the GCD of any three numbers, seriously, just pick any two of them at a time and take two at a time, find the GCD, and then take that GCD and see and compare it to the next number. So what they've done here is they've really tried to say, hey, wouldn't it be great with 6341 and 6339 that basically these two numbers right here are so close together, it's virtually impossible for them to have the same multiple. And so that's what they come down and show. They show, hey, between these two numbers, the last two numbers here, there is no common multiple. So the GCD is 1. And that means it really doesn't matter how big that first number is because there will be nothing in common left over. All right. So now, now we get to something that is known as the least common multiple. This is the pairing with the greatest common divisor. Remember, divisors divide into a number, and therefore divisors are smaller than or equal to the number itself, whereas multiples are like kind of copies of the number. So a multiple will be typically larger than the number you start with, unless you have a multiple of 1, in which case it's exactly the same. So let's go back to what we did initially, which was 24 and 36. Let's just kind of show that one more time. There's going to be a really nice connection here that I think is going to help immensely. Immensely. So we had 24, which was 2 cubed times 3. We had 30, which we saw was 2 times 3 times 5. We saw that the GCD is the biggest, is the smallest exponent for each of the factors. So I could put a 5 to the 0 here. So the GCD would be 2 to the first times 3 to the first times 5 to the 0 if I put everything down there, which is just the number 6. So now let's start talking about multiples. And when you think about the number 24, 24 does have multiples, 24, 48, 72. If you want to find these, grab your calculator, type 24 plus, and then put 24 equals, 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 equals. Just keep hitting equal signs. It'll keep giving you more groups of 24. So 24, press equals, plus 24 equals, 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 and you can continue making a beautiful sequence of 24s, 120, 144, 168, okay, 192. I'm just going to put a few more down, 216, the next one, 240, and I could keep going. Okay, now let's make multiples of 30 down here. So 30, 60, 90. This is a little bit easier, right? 120, 150, 180, 210, 240, 270, dot, 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 dot. Okay. And now look at these two sequences. Do they ever overlap? Do they ever have anything in common? And take a look. They do. They do have something in common at 120. They have something else in common again at 240. If you kept going, this shouldn't be a big surprise to you, but if they match at 120 and they match again at 240, they match again after another 120, which forms a sequence of common multiples. The common multiples are 120, 240, 360, 480, 600, dot, dot, dot. You get an arithmetic sequence of all the multiples that are common multiples of 24 and 30. Okay. Now, you'll notice that sequence continues going up, right? By 120 every time. So if we're talking about, hey, what's the greatest common multiple? I've got a sad face for you. because the greatest common multiple, it just doesn't exist, because I can always find one greater than whatever you think the greatest common multiple is. So that's why we don't have a greatest common multiple. But we can have a least or smallest common multiple, and that would be 120. So the least common multiple would be the number 120. Now, if you do prime factorization on the number 120, you'll see that you get, what is this, 40 times 3? Okay, 40 is 8 times 5. So I get 8 times 5 times 3, which would be 2 cubed times 3 times 5. Now, I want you to take a look at this because this is what's really cool. Remember how the GCD, the exponents that you chose were the smallest exponent in prime factorization? Look at the factor of 2 up here. There's 2 right there and there. And this one needs a 3, which is the largest. This one needs a 1. I already used up one of the ones, so I'll use up the other one. And then I need a 5 to the first, which is the largest. So for the greatest common divisor, you pick the smallest exponent on those numbers, on those shared primes. For the least common multiple, you actually choose the biggest one because we need it to be a multiple of, and that's how you get 120. Okay. Perfect. And there's something else that I think, I guess I should say, is kind of not surprising when you think about it, but sometimes you miss it because you're too busy kind of doing a process. And since I get to teach at least for a little while longer, I'm going to try to make sure you see the cool things. If you look at this number, it's a 2 cubed times 3 with no 5s at all in it because it's the number 24. My LCM is 2 cubed times 3 times 5. So 120 is 24 times 5. So what does that mean? It means these numbers overlap every fifth multiple. So if you're counting, you go 1, 2, 3, 4, bingo, 5, 6, 7, 8, 9, bingo, 10. So that's where you're going to have those common multiples. And likewise, the number 30 has only one group of 2, whereas 24 has 3 groups of 2. So when you look at 120, you could write as 30 times 4. And so this is saying every fourth multiple of 30 is where they will overlap. So if you count, you say 1, 2, 3, 4. 1, 2, 3, 4. And you will always have these numbers matching up with these sequences. So to me, that's super cool. And also, I want you to think about this. If you chose the largest exponent for the LCM and you chose the smallest exponent for the GCD, that means you've actually chosen every possible exponent along the way. And what that means is we can connect it in this following way. And to me, this is like super cool now. All right, watch this. This is a quick way of relating the LCM and the GCD. Okay, the LCM is 120, the GCD is 6, and what I'm going to do is I'm going to have you multiply those together. 6 times 120 turns out to be 720. Okay, now get this. Take 24 and 30. 24 times 30, guess what it turns out to be? 720 as well. Okay, so now why is this so cool? This is so cool because it means if I can find the GCD quickly, like with the Euclidean algorithm or anything like that, I don't have to go through and find the least common multiple with one of those other long methods. I can find it very quickly. So here's the idea. I can look at 24 and 30, and you could say to yourself, 24 and 30, what do they have in common? We know they have a 2 in common, right? So break that down. The 2 goes into each. That leaves me here with a 15. That leaves me here with a 12. I can see a 3 that goes into each of them. Okay, that leaves me here with a 5. That leaves me here with a 4. Nothing goes into a 5 and a 4. So my GCD is 3 times 2, which is 6. So what I can do is I can come over and I can say 24 times 30, that would be this number right here. And 6 times the LCM, if I don't know what it is, has to be that same number. So this is going to equal 6 times my LCM, and I can just divide by 6 on both sides. I'm not even kidding. And you will have the LCM sitting there by taking 24 times 30 in your calculator and then divide by 6. Now, if you prefer, you can reduce because you know 6 has to go into these and just have 4 times 30. You'll get an LCM of 120. That is how quick this can work. Okay. So again, is it super quick? To me, yes, it's super quick. If you wanted to try another one, sure. We just did 180 and 168 not too long ago. And the GCD of those two was the number 12. 12 went into each of those. And nothing bigger went into each of them. So 12 goes into each of these. If I want to find the LCM, what I can do is I can multiply those numbers together and just divide by 12. So if I grab my calculator, this is going to be so much quicker than doing the other techniques. To the 180 times 168 gives me a huge, like 30,000. Just divide by 12, and you will have the least common multiple. The least common multiple is 2,250. So again, a lot of quick ways. I am trying to show you some efficient ways of doing not just the homework, but of thinking about these concepts. Okay. So can you line things up on the number line? Of course you can. Feel free to go to town. Um, but think about this. The number line might work really well with smaller numbers. It's not going to work that great with 180 and 168 because how many multiples would it take for me to get all the way there, right? Again, with smaller children, you can do it with the colored rods or what are known as Cuisenaire rods or C rods. You can continue with that. You can do the intersection of sets method, which is great. What a great technique. But you'd have to list all of these out every time. And for numbers like 180 and 168, it's going to be very problematic. So again, not like it's a bad way, just might be a longer technique. Okay. There's the prime factorization method. What we said with prime factorization is I find the biggest multiple, okay? Because that's what I want, the biggest exponent. So here, if I was looking at 3 numbers, that's fine. I would find a 2 squared, a 2 squared, and a 2 cubed. In my common multiples, I put 2 cubed. I have a 3 cubed, and a 3. Got it. I'm using 3 cubed because it's the biggest exponent. And lastly, I have a 5 to the 1. The others don't have any 5s at all, so I throw a 5 in there, and there's my least common multiple. So prime factorization, again, is significantly faster. You're going to love it, but you do have to get there. All right. This last little theorem is the one I already demonstrated, that the GCD of two numbers multiplied by the LCM of the two numbers has to be A times B. So what's great about A and B, remember, no matter if they have prime factors in common or not, is the LCM will choose the bigger of the exponents. The GCD will choose the smaller. So when you multiply, you have both the bigger and the smaller, which is exactly what you have when you multiply the original numbers together. Okay. They do talk about using the Euclidean algorithm, but not to find the LCM. You use the GCD, find the Euclidean algorithm, get the GCD of 17, and then you just multiply the numbers and divide by 17 to get your least common multiple. Again, look at this number, 40,936. In order for me to find that those match up, I'd have to write 731, then 1,462, then 2,193. And again, I have to write out all the multiples of 731 until I got to 40,936. So it's way quicker to do something like this. Okay. All right. So anyway, there we go. Now there is a problem here that this one's probably near the top end of what could be expected of you. It's if I tell you the GCD and the LCM, can you find all possible numbers that could make that work? And because of the connection between prime factorization and each of these, it's just easier to write out the prime factorization. All right, so that does it. That takes us into the homework, right? So that's it for section 4-3. I do want to point out one quick fact. The multiply the two numbers and divide by the GCD, that works with two numbers. You'll notice there was no theorem that said it works for three numbers, and that's because with three numbers, you don't just have a largest and a smallest. You might have a middle number, but the GCD and the LCM, those are just two numbers. So you'll only include the biggest and the smallest. You're not going to include the middle one, so you can't multiply the three numbers together and get the same thing. So it's just not going to work, and you can do a counter example if you need to demonstrate that. All right. I'll come back with a homework video over a few of these. We'll pick some of the ones out of part A that are very similar to part B, and hopefully that gives you what you need as you go forward. All right. Pretty cool section. That's the last one before the test. All right. Off you go.